All right. So in order to deal with this, we're going to define a new coordinate system, which is a coordinate system of the plane. And this is going to be called the DSN coordinate system, where the D stands for dip. It's going to be a vector that goes along the tip of the fault. I explain a bit what is the dip, okay? But it is that vector over there. It's contained on the plane and goes with the name N. The second one is the strike. And the strike is going to be that vector, and we're going to call it NS. And there's one more, which is a normal. But let me ask you, in which direction should it go if we are dealing with a right-handed coordinate system?
Out of the page.
Out of the page, right? So I like doing this with it. So dip, strike, in towards the left, normal up, right? So whenever you have fault, this is a fault plane, then the dip is going down. This is going to be the strike, your middle finger, and this is the normal vector. So the normal is going to go up. And these are perpendicular to each other. Okay.
What is that symbol? Like when you go out of the page, there's a circle with a dot in the middle, something like that?
Which one?
How that, like when the arrow is out of the page, you will draw a circle.
Oh yes, but that's when we're looking in 2 dimensions, and you cannot see the 3rd dimension.
Okay.
Then to draw a vector, just do a circle and a point.
Okay.
But this is not the case because this is a 3-dimensional flow. Okay, so let's talk about dip and strike. Dip is going to be the angle between the horizontal plane and the plane of maximum slope for a given plane. So for example, if you imagine this plane in 3 dimensions with gravity going in the direction D, if you were to drop a drop of water here, the drop of water will go this way, through the path of the maximum slope. And the angle between the horizontal plane and that path is what we call the angle of dip. And for example, for this particular plane, you could say this plane or this fracture, for example, is dipping 30 degrees towards the southeast, right? That's what you would say from that. And that's not enough to characterize a plane. You also need a second angle, which is the angle of strike. And the angle of strike is the angle between the north and the intersection of the plane under study with the horizontal plane, which in this case is that line. That line is the intersection between the horizontal plane and this plane. That may extend above and below what I drew, but that's going to be the strike. With these 2 angles, you fully characterize the direction of a plane. And similarly to the matrix RPG, you're going to be able to write 3 vectors with their components in the geographical coordinate system. Well, let's do it in order. E, S, and N. Where the numbers that go inside depend on depend on the angles of strike and dip. I'm not going to write the equations here because it's just a bunch of sine and cosines that we don't have to repeat again. But for reference, you can find them over here. So there you go. And D, and S, and NN, strike, dip, and these are the numerical values of NN, NS, and N.
Can you explain again, like
yes.
the dotted lines for the depth? I can't visualize it.
The line, so for example, with this dashed line, what I mean is that that line will be a line on a horizontal plane.
Within which coordinate system?
The geographical coordinate system. So on a plane which contains the north and the east, that horizontal plane contains this line.
Okay.
And the angle between the line of maximum slope of that plane with the horizontal plane is the angle of dip. Right?
Yeah.
So you know, physically, if this is the plane, and this would be the horizontal plane, the dip would be this angle. Okay?
I'm sorry, what's NN?
NN is a vector which is normal to the plane that we're dealing with. So it's perpendicular to the plane. So ND and NS are on the plane.
Yeah.
ND is in direction of dip, NS in direction of strike, and NN is perpendicular to those two, therefore it's perpendicular to the plane.
So it's coming out towards us.
In this case, yes.
I see. NN vector perpendicular to plane.
Okay, so what do we do with that now? Our objective is that given a state of stress, let me draw that plane again. Given a state of stress, we would like to compute what is in direction normal to the plane. What is the normal stress in direction of the strike? Let me change a little bit the direction of this so it looks more 3D. Okay, that's normal to the plane, but in addition to that, we're going to have a component which is going to be on the plane, and it's going to be the shear on direction of the strike, and also, since now the plane in itself is a two-dimensional entity, we're also going to have a shear in the direction of the dip. And if you add those two, you're going to get the shear combining the amount of strike and amount of dip. And that's going to be a vectorial summation. All right. So how do we calculate now these three? We're going to utilize what we did that class, last class, which is this equation. And the first thing that we're going to do is we're going to calculate the traction vector T, where the same as before, T is going to be stress times the normal vector, but now we have different names, okay? The one before was a general equation. Now we have to apply it to the geographical coordinate system. So here we're gonna use SG, and we're going to multiply it times the normal vector, which is N. We have SG, we have NN, we just defined it, so we know what is T. If I want to compute the value of Sn, the numerical value is going to be the traction vector T projected on the normal direction. And that means in linear algebra, a dot product with the vector Nn. That's going to be Sn. If you want to compute effective vertical stress, effective normal stress, sigma n, you just do Sn minus the pore pressure. We don't need this one anymore, so let me wait again. What is going to be tau d? If you make an analogy of this with Nn, what do you think tau d is going to be? We're going to need the traction vector for sure, t. But in which direction are you going to project t? In the direction, if it's tau d, it's going to be in the direction of the t. So it's going to be nd. And tau s is going to be t times ns. And from here also, if you wanted to compute what is the total tau, the numerical value is going to depend on tau d, on tau s through the Pythagoras equation, because it's a vectorial summation.
The Pythagoras.
Oh, Pythagorean.
Yeah, c
So
squared.
we have tau d, we have tau
b
s,
squared
Square
and this
plus,
is the
everything,
total
and then
tau.
because there's two
Tau.
triangles there for tau.
Okay.
The exponent is z, right?
So Pythagorean theorem.
Say again?
The exponent is z.
It's
Oh,
no,
just one
this is
triangle.
This is my number
Yeah.
2, I'm sorry.
But with the
my
vectors,
number 2 looks like it's
there's
it's
two.
square.
Interesting.
Oh,
Okay.
okay.
Okay, so
So
we
this
just
is
square
just
both
Pythagoras.
values
Yeah.
and together, take the square root to find
So-
Okay.
just just tau.
Let's try to understand the
Exactly.
physical meaning of this. This is going to be very useful because now in 3 dimensions we have 2 taus. We have 1 sigma n or 1 Sn, but we have 2 taus. For example, if tau s were to be equal to 0, that means that there is no shear stress on this direction, and there is just tau d. So that would mean, for example, we're talking about a fault that is sliding either up deep or down deep. If it's down deep, it's going to be a normal fault. If it's up deep, this part is going up deep, there's going to be a reverse fault. If tau d is equal to 0, that means that the fault is not moving down deep or up deep, but just moving along the strike. And either it moves like this, that's going to be
Left
something
lateral.
called left lateral, or it moves like that, that's going to be right lateral.
Yeah.
And the value of tau s and tau d are going to tell you that. And the signs are going also to be important because if tau deep, for example, here is positive, that's going to mean that it's going down deep. If it's negative, it's going up deep. And a similar thing for the shear. But I never remember what is left lateral and right lateral. But it doesn't matter, okay? It's just a convention. The important thing now is that we have two taus. And that those tell us in which direction the fracture or fault might potentially move. So, coming back to the 3D Mohr circle, these two values were the ones that, for a given state of stress, sigma 3, sigma 2, sigma 1, were the ones that you have to calculate and were inside these three circles, sigma n and tau. So if I gave you a fault or a fracture with a given strike and dip, using all the linear algebra that we just showed, you can calculate this point. And you can tell where that is in that 3D Mohr circle. And that's exactly what you have to do for this project. You know what is the state of stress because it's from the previous homework. Also, first I'm going to tell you to generate 100, or if you want to do more, just do more, but at least 100 randomly generated faults with a given strike and dip. For each of those, you have to compute sigma n and tau and plot it in a 3D Mohr circle. And after that, I would like to know if